All right. Can people hear me okay? Yep. Okay. Well, I'm super excited to be here. I am Johann Schleier. I am CTO and co-founder of ifwe. And I'll be telling you a little bit more about what we are doing there in a few moments. But I want to start out by introducing this idea that we've been doing for a couple of years, and it's an agile approach to machine learning, and specifically with an emphasis and a focus on real-time recommender systems. Now, let me give you a picture of how we believe things should work. They don't always work this way, but they should. So let's just see here. Okay. All of you have a good understanding of machine learning today. So you start out, you gain that understanding of the technology, then you gain an understanding of some problem that you're trying to solve, and you want to be able to put those together. You have some inspirations. You have some opportunity that you see to make your product better. So naturally, what do? You go ahead and you create some training data. That might mean going to your data sources, whatever they are, maybe a relational database, running some queries, extracting some features that you think are interesting inputs to a model, and then training with one of the great number of predictive tools that are available, be that scikit-learn or R or Vopal or all sorts of other things, things in the Spark ecosystem, proprietary tools, lots and lots of great tools for training predictive models and doing data science. And then you go and you put those models in production, see improvements, and what we would like to do if we are a learning company is we would like to iterate on this. So go right back up to more opportunities, perhaps inspired by what we've learned, and run through this cycle, much like we run through the cycle when we do web development, doing daily releases, constantly testing, iterating, and updating. Now, the reality is that when we are working with machine learning, it's often not that easy. Certainly wasn't that easy for us. So we create those aggregates, train the models. That usually goes pretty well. But when it comes to going to production for real-time recommendation systems, this can be really, really painful. We talk about rewriting things so that we can make predictions against perhaps millions of candidates in a small fraction of a second. It means going from batch jobs to rewriting in Java or Scala or other high-performance languages. It means going from work done by data scientists, perhaps, to work done by data engineers or people with real experience and performance. And this is it's a real bummer, I think, and something where I believe that we can do much better, and in fact, if we have been doing much better. So by the time we get to those improvements, we say, often, was that worth it, even with very smart people working on it? So what is ifwe? ifwe is working on where we see opportunities for game changers in social apps. Most recently, we saw it in over-the-top messaging. Before that, it was social networking. And the two profitable businesses that we run today, Tagged and High5, are from that social networking era. High5 was once the second largest social network in the world after MySpace. Facebook has now dominated that. But what we pivoted to is social discovery. And social discovery is all about connecting people who should know each other but don't yet. And you can see there's a big recommendation challenge there. So this is the real-time recommendation challenge, or rather one of them, that we work on at ifwe. It's the tag dating feature. So this may remind many of you of Tinder. We open the app, and you have some number of recommendations that are presented. You can either swipe yes to say this is somebody who I'm interested in connecting with, if that person is also interested in connecting with me, or you can swipe no. Our version of this launched 2008, and it has something like 10 million candidates to select from, so that's our recommendations challenge there. The updates are coming in very, very fast, so in excess of 1,000 updates per second. There will be many millions of updates during the course of this brief presentation, and we will be evaluating billions, actually probably tens of billions of potential matches, sort of pairwise in the network. So there's also a need for real time, and that's the real emphasis here, being responsive to current activity. We have sessions that last maybe a minute and a half, and it's very important that we are learning what's going on with that user and their preferences in the course of that session. And then, of course, like anything on the internet, they expect that search to return anything that might possibly exist that matches them in a very small fraction of a second. So let's go to the implementation pain points. Again, that handoff between a data scientist and the software engineer, potentially the need to translate features from SQL to Java, that batch processing, which is painful and not really real-time. You may have to rethink the features. If we had a feature that was, say, how many times did the user do X, Y, and Z in the past week, once we go to real-time recommendations, that actually may not be the right metric, right? It may be in the last minute. And so there's a mismatch there. Also the need for high performance in-memory data structures. So what I'm going to assert today is that this approach is a little bit broken, and that really it's time for some new thinking, that there really is a much better way. And in fact, we have been able to iterate very rapidly at ifwe, doing real-time recommendation engines, and there's a set of proprietary technologies that we've developed to do this. I'm going to tell you a little bit about them and also about an open source project that we are starting to work on to make this approach more available. So, one way that works better. Okay, focus on these steps here, 4 through 6. And I'm going to rewrite them just a little bit and talk about creating interesting features. That's really where the magic is in the data science. It's in taking some thing that happens, some data, and mapping it into a format that's very natural for that machine learning algorithm. So for example, the features for dating might be looking at how often does this user connect with someone who's in the same city versus the next city over? How about age difference? We can keep coming up with all sorts of ideas. And for us to do agile machine learning, what we want to be able to do is we want to be able to have that idea, train it, get it in production, verify with real users that it continues to be effective, and we want to iterate that cycle, and we want that to be super, super rapid. And as I mentioned before, we have great tools for training those predictive models, but putting them into production is really where the pain point is. And in fact, creating interesting features and then putting those features into production, that feature engineering is really the key, and that's where our emphasis is. So my assertion is that if you want to do real-time machine learning, and if you want to iterate on that rapidly, it really matters how you structure the data. I think a lot of you are probably aware that you can get a huge advantage just simply by collecting data in a format similar to the one that you want to analyze or train with. And I'm going to sort of go one step further here and insist that it's event history that is the right way to look at data that really has some huge advantages. Now, some of you may say, well, we collect data events all the time. What's the big deal? Oftentimes, we collect data in terms of events because that's just a very natural way to generate them, particularly in a consumer product. But once we start to analyze them, we go very quickly to these aggregates that are the step that occurs before we present that to the machine learning model. So this is the way, really the only way, that I ever want to see data in the context of real-time machine learning applications. So there's some history. It's everything that happened, all of the events. And then I want to go ahead and take some time range. I'm going to take some start time and potentially an end time if I'm doing training. But if I want to do real-time recommendations, that end time goes into the indefinite future. And then every time something happens, I want to update my model. Okay? So this is a format that's pretty natural. In fact, a lot of the tools that we use, even pretty good stuff, Kafka and so forth, Hadoop, it's not necessarily supernatural to access your data this way. You can do your real-time data this way, but then historical data, it's going to take some sort of a little bit of extra effort, some extra gymnastics. So this has really helped us a lot, and I'll talk in more detail about it. So again, I'm going to come back to this insistence that everything is an event. Okay, California is in the U.S. All right, well, 1848 or 1850, depending on which you count, it actually became that way. And it really helps to structure it. That example might be a little bit of a stretch, but let's take IP address, you name it, is in California, we know that that is sometimes the case and sometimes not the case, and it's going to change. Here is an example of some practical events from our application. A user is registering and setting up a profile. Well, that profile information is going to change. Sometimes people lie about their age, and then they change it later. They change their photos. They change what's written in the profile. If we have that information as reference data, which can sometimes be more natural, particularly if we take it from the online system that's running the product, we're going to have trouble reconstructing a historical state accurately. So a lot of other sorts of updates are rather natural in terms of events, but some aren't, and it's really important that your model is always consuming in terms of events. So here's a simple class that describes what it looks like. I'm going to start showing a bit of code. This is Scala code. Are people here Scala people? Some people? Hands up? Okay, well, if you're not a Scala person, it's actually really easy to learn the basics of it, which is all that you need to work with this sort of approach. So there's an update function for the model. This is the only way that the model knows anything about the world. It gets events, and it gets them in time order, and it updates. And then there's some scoring, so the context might be which user is asking for recommendations, maybe what that user's filter settings are, what that user's query is, and so forth, and then it'll just give me the top end. So this is what models look like, and the models, they consist of what? Of a bunch of features. So features similarly are related to state. So each feature might have, for that particular candidate that we might recommend, or for that user for whom we might be making a recommendation, some internal state that's relevant to that feature. Again, examples would be the age difference between users, or whether certain profile fields are matching. They could also be some output from an unstructured or from an unsupervised learning technique where we've done some sort of clustering. And we might ask whether users are in the same cluster. We might run some link prediction. We could do all sorts of things in the features. The key thing is that they learn about the world through events, and then there's some context for scoring candidates. And a whole bunch of features get combined. We can weight them using logistic regression or combine them with random forests. Those are two techniques that we commonly use, and that's how the model ends up scoring. The really good models are those that we can iterate on quickly, where we can iterate with teams. So one data scientist may be working on one feature while another is working on another feature. We can combine that effort really naturally, train, and iterate. So let's talk about how training works. We want to generate training data, and one of the things that one has to be careful about with the aggregates, if you're, say, querying with SQL to generate your training data, is you need to be really careful that you don't introduce some knowledge from prior to that outcome into your training set. When you're working with event history, it's supernatural. Before that event gets updated into the model, we look and see what is the state of the world and write the outcome. There's no way to cheat. There's no way to look ahead. So I'm going to do a live demo in just a moment, and I'm going to switch data sets. So in order to show that this approach generalizes, what we've done is to grab a Kaggle competition, which is a Best Buy data set. There's a product catalog of video games, and there is a set of data from users who go on Best Buy on their mobile site, they query, and then they click on some product. And it's our aim to predict what that user is going to click on, and we can use that text query. So here's roughly what it looks like. All of the updates to the product catalog, those are events. So there's some name of the product, some description, a SKU number. And then there's this event data for product views. A certain product was viewed following a certain query, and it happened at a certain time. So let's go ahead and build a model. So this is interesting because we have usage history, but we also have a text problem. So let's look at what this framework looks like. Now, this is an adaptation. This is open source, by the way, on ifwe's GitHub account. We have a model, and there are some of these update extractors, essentially. So you can see whenever a product is viewed, this will match. Whenever a product is updated, this here matches for the different types of events. And for those of you familiar with Scala, this will be sort of very clear for the rest of you. Hopefully you can get the general idea. So what I have defined here is one feature. This is just the overall popularity. What's been viewed the most? It's a natural thing to consider as potentially one input to the predictive model. So what I want to do now is I want to go ahead and define another feature that is going to tell me what is most popular for a given term that was entered, which SKUs were most popular, okay? So I'm just going to go ahead and create a new feature. And this counter is a primitive. And we want to count sort of for the query terms and the SKU viewed. Let's just see how many there were, okay? And then we need to define this scoring method. And that's going to be a function. So let's first get the terms. So we're going to do a little normalization here just to make sure that strange characters are removed. And then we're going to get the individual words. Let's see, that may be low on the screen for some of you. Then we're going to define a mapping. And we're going to take each term. And what do we want to do? We want to look at the popularity of that combination of ID and term. Sorry, terms not map. And then I'm going to avoid division by 0. Okay? And then we're going to take a whole bunch of these, and we're going to multiply them together. Okay? So this is a really simple way. We're using these primitives, these counters, and there are a whole bunch of other primitives that we can come up with, but counters are actually pretty practical, and ratios of counters with different sorts of filters allow us to define just a tremendous variety of useful features. So let's do one more. Let's go ahead and do a term frequency inverse document frequency. So this is sort of the natural information retrieval approach that you would take. So we're going to define another counter. And in this case, we don't want the views, but we want those product updates. So we want the product updated named terms and then the SKU updated. Okay? So term frequency inverse document frequency. Who can tell me what it is? So I'm going to want to know how many times is that term in that document. I also want to know how many documents have that term. So I'm going to create sort of a hierarchical set of the term and the document. And then I also want to just see how many documents there are altogether. That's going to be useful for me as well. Okay, so let's go ahead and implement a scoring function. And I'm going to take those terms, again, from the query. And I'll also just get here the total number of documents, go ahead and compute that ahead of time, and then define a mapping. So the term frequency actually, let's and the document frequency is going to be now the number of documents that have this term. Okay, and now we need to combine these. So Lucene has a particular way of combining them. There are a variety of others in the literature, but we're going to take the square root of the term frequency and we're going to multiply it by the square of 1 plus the log of this particular expression, and then let's go ahead and sum those all together. Okay? So we now have two features, a term popularity as well as a term frequency inverse document frequency against the catalog. We'll go ahead and add them. Okay, they're in the model. So now let's go ahead and see if I did this right and see if we can run it. So I'm in SBT, I'm just on a shell, and I'm going to ask it to generate some training data. It's going to go ahead and step through time, write out those training events to a file, and I'll just have a look at that. So here you can see a bunch of ones. That's the product that the user selected, and then we choose some other some other product. This is in the very left column here. Some other product that the user didn't select as another training example, okay? And so we have a file, a whole bunch of this stuff. Now I'm going to go ahead and run R, and I'm going to just run a logistic regression. You can see that we have these 3 features popping out, and in a normalized sense, it's actually feature 2, which is the popularity for that term, actually from the usage as opposed to the product catalog. But we have a lot of statistical significance on all 3. And what we can do is we can grab those coefficients now and pop right back in to the program. I'm going to just hard code in some of those coefficients, and let's go ahead and run scoring. Now, it's going to jump ahead to a different time period beyond that for which I trained, and we'll just see how well we do. We're going to produce for each user 5 possible products that they might want to click on, and in fact, if they do, then we get a point. You can see here 84.4%. So really super quick implementation, and the great thing here is that we're able to write that model just once and train using that one representation of the model, deploy to production, and then just iterate. So a very, very rapid cycle. It allows multiple people to work on that same problem at the same time. So if one of my colleagues comes up with another feature, we just drop it right in. We're in Scala, so we have a great deal of expressiveness, and in general, that's been our greatest priority. We also work on performance because we do need to rank so many possible candidates in a fraction of a second, and also perhaps when we update these models, when we do our training, we may be playing back over months. So performance does matter as well. And then scalability is also of interest and concern. All right, so that's the demo. And I really just want to emphasize now this approach here, this loop. I've talked about that. That we're able to just do these fast cycles. 2 weeks is very typical, and in fact, there are people on our team who would like to do all of this in the matter of an afternoon. I think that really what's most key, and that's missing from a lot of approaches, is this insistence on structuring the data and accessing the data, importantly, in terms of event history. This is Jerusalem, and Jerusalem is a city where they say you can pick your century just by walking around from one neighborhood to another. And that is what we do when we work and do machine learning with event data structured in the form of history. We can jump to a point way in the past, we can roll forward, generate training data, validate that training, and then just roll right on into the future and make real-time recommendations. So it's a very powerful approach. It's the only way I ever really want to access data. And so that's sort of the key takeaway here. There are some other little bits of learnings that are important as well. Sampling to avoid feedback so that you don't have your results of the last iteration of the model biasing your training for the next iteration. A real emphasis on those features being kind of live and personal and providing that personalization, whereas the coefficients of the model, those can actually be static. And we really put our emphasis on engineering those features rather than perhaps worrying about which machine learning technique we should be using. So thank you all so much. We have code open source on GitHub, and I encourage you to try it out. All of this demo code that I ran is there. This is sort of a toy implementation, I would say, but it's moving towards a public and open source release of the technology that we are using all the time. That's a proprietary technology that is serving us very well. So thank you all so much, and I would welcome your questions at the coffee break.